The morning of May 14th, 1945, USS Enterprise, the most decorated warship in American naval history, steams 70 miles southeast of Kyushu with Task Force 58. Admiral Marc Mitscher's flag flies from her main mast. Her radar operators track Japanese aircraft probing the perimeter, searching for gaps in the combat air patrol. At 6:53 a.m., the call comes over the circuit. Bogey inbound, low altitude, using cloud cover. Lieutenant Junior Grade Shunsuke Tomiyasu has been flying for 90 minutes, hugging the wavetops, darting between clouds, watching American fighters streak past overhead. His Mitsubishi A6M Zero carries a single 550-pound bomb strapped beneath the fuselage. Enough fuel remains for maybe 10 more minutes of flight. He won't need more than that. Breaking through a cloud bank at 1,500 feet, he spots Enterprise below. The massive carrier is turning hard to port, her 5-inch guns tracking his approach, 40mm Bofors hammering the sky with bright tracers. Tomiyasu pushes the stick forward, diving at 30 degrees. 200 yards from the ship, he executes a snap roll, flipping the Zero completely inverted, steepening his dive to 45 degrees. The maneuver is perfect. Anti-aircraft fire that was tracking his original trajectory passes harmlessly through empty air. At 6:54 a.m., the inverted Zero plunges through Enterprise's flight deck just aft of the forward elevator, slightly to port of centerline. The bomb detonates high order, 8 feet below the flight deck. The explosion vaporizes everything within a 20-foot radius. More critically, it detonates directly beneath the forward centerline elevator, a massive platform 60 feet long by 48 feet wide, weighing approximately 15 tons. The blast wave hits the elevator from below like a hydraulic ram. Steel cables snap, support girders shear. The entire elevator platform, along with 3/4 of its deck plating, rockets straight up through the opening in the flight deck. Sailors on nearby destroyers watch in horror as the 15-ton elevator climbs 400 feet into the air on a column of smoke and flame before tumbling into the Pacific. Pieces of the elevator framework, brackets, and steadying rails crash back onto Enterprise's flight deck, forward and aft of the now gaping hole. 14 men die instantly. 68 more are wounded. 3 officer quarters surrounding the elevator are simply gone. The blast wave continues aft through the hangar deck, blowing out compartments back to frame 140. Enterprise doesn't slow. She doesn't break formation. Her crew fights fires, treats casualties, and maintains station with Task Force 58, but her fighting efficiency is gone. With a 60-foot by 48-foot hole punched through her primary operating surface, with her forward hangar access destroyed, with structural damage from the blast extending across the entire width of the ship, Enterprise is done. On May 16th, she withdraws from combat for the final time. The most successful carrier in the Pacific War has been knocked out by a single kamikaze. Not because her armor failed or her damage control faltered, but because a centerline elevator, by simple necessity of its engineering, created a catastrophic vulnerability that no amount of bravery could overcome. The problem wasn't unique to Enterprise. Every aircraft carrier commissioned before 1940 had the same weakness built into their basic architecture. Centerline elevators, massive platforms that moved aircraft between the hangar deck and flight deck, sat directly in the middle of the ship's primary operating surface. When the elevator was in the down position, servicing aircraft in the hangar, it left an enormous hole in the flight deck, a hole that compromised the structural integrity of the entire deck, a hole that, if the elevator was damaged or destroyed, couldn't be covered, couldn't be worked around, and effectively turned half the flight deck into unusable space. Naval architects had understood the problem since the 1920s, when USS Langley, America's first carrier, converted from the collier Jupiter, demonstrated both the utility and the limitations of carrier aviation. Langley had a single centerline elevator, 36 feet by 40 feet. When it was up, the flight deck was complete. When it was down, there was a hole. Simple geometry. Impossible to avoid. The elevator had to be large enough to accommodate the wingspan of the largest aircraft aboard. It had to be positioned where it could efficiently move planes between decks. And it had to pierce the flight deck, the ship's strength deck, creating a structural discontinuity that weakened the entire vessel. The Lexington and Saratoga, commissioned in 1927, each carried two centerline elevators. The Ranger, Yorktown, Enterprise, Hornet all followed the same pattern. 2 or 3 massive elevators punched through the center line of the flight deck. The design made operational sense in peacetime. You could spot aircraft efficiently, move them below for maintenance, bring them back up for launch. The hangar deck remained centered beneath the flight deck, protected by the hull. Everything was symmetrical, balanced, conventional. Then came combat, and the conventional wisdom started killing people. At the Battle of the Eastern Solomons in August 1942, Enterprise took 3 bomb hits during a 5-minute attack by Japanese dive bombers. The first bomb pierced the number 3 elevator at the flight deck and detonated 42 feet below between the second and third decks. The elevator was disabled instantly. The 72-foot by 48-foot hole left in the flight deck remained unusable for the rest of the engagement. Enterprise's deck crew had to work around it, respotting aircraft, managing launches and recoveries with effectively 20% less flight deck. The ship survived, but the incident revealed something naval planners had been quietly worried about for years. An elevator didn't have to be destroyed by enemy action to become a problem. It just had to be in the wrong position at the wrong time. If you needed to launch a strike and the forward elevator was down bringing up aircraft, you lost that entire section of deck space for launch operations. If you needed to land recovering aircraft and the aft elevator was down, you lost arresting wire positions. The flight deck wasn't truly a continuous operating surface. It was a series of smaller surfaces interrupted by massive movable holes. The maintenance burden made things worse. Centerline elevators were enormously complex pieces of machinery. Each platform was supported by a framework of girders and cables extending down through multiple decks to machinery spaces deep in the ship. Hydraulic pumps, electric motors, control systems, safety interlocks, all of it required constant maintenance. The Navy estimated that each centerline elevator consumed roughly 500 man-hours per month in preventative and corrective maintenance. For a ship with 3 elevators, that meant 1,500 man-hours monthly, pulled from a crew already stretched thin running flight operations in a combat zone. And if something went wrong, if hydraulics failed or cables frayed or machinery jammed, the repair work was brutal. The elevator machinery spaces were cramped, hot, difficult to access. Parts had to be fabricated or requisited from supply ships. A major elevator casualty could take days or weeks to fix, during which time the carrier operated with reduced capability. Task force commanders learned to work around elevator problems the way infantry officers worked around supply shortages, accepting degraded performance as the cost of doing business. But the real nightmare scenario was battle damage. If a bomb or kamikaze hit an elevator directly, as happened with Enterprise, the explosion wasn't contained. The elevator shaft became a chimney, channeling blast effects up and down through multiple decks. Fire spread through the opening. Structural members that supported both the elevator and the surrounding flight deck failed simultaneously. The damage cascaded, turning what might have been a localized hit into a catastrophic destruction affecting the entire forward or aft section of the ship. Carrier captains started requesting that their ships steam with elevators in the up position whenever possible during combat operations. Keep the flight deck solid, accept the reduced hangar access. Better to have a complete flight deck with inconvenient hangar operations than a perforated flight deck with easy hangar access.
But this created its own problems. Aircraft that needed emergency repairs or rearming had to be worked on the flight deck, in the open, exposed to weather and enemy attack. The hangar deck, theoretically the protected workspace where major maintenance happened, became harder to access. Efficiency dropped. By mid-1943, the Navy had compiled enough battle damage reports to quantify the problem. Carriers with centerline elevator casualties saw their effective sortie rate drop by 30 to 50% until repairs were completed. Ships that suffered elevator destruction effectively lost 1/3 to 1/2 of their flight deck utility. The USS Yorktown at Midway, the USS Wasp at Guadalcanal, the USS Hornet at Santa Cruz, All demonstrated that centerline elevators created single points of failure that could cripple an otherwise functional ship. The solution had been sitting in Boston Harbor since April 1940. USS Wasp, a one-of-a-kind carrier built to use up the remaining tonnage allowed under the Washington Treaty limitations, had commissioned with something no American carrier had ever carried before: a deck edge elevator. Not centerline, not punched through the flight deck. Edge-mounted on the port side, forward of midships. The design was radical enough that many in the Bureau of Ships considered it experimental. Wasp displaced only 14,700 tons standard, significantly smaller than the Yorktown-class carriers. Her designers, forced to maximize capability within treaty restrictions, had to get creative. A centerline elevator consumed hangar space below decks and required structural support that added weight. An edge-mounted elevator, positioned outside the normal hull contours, could theoretically save both space and weight while increasing effective deck area. The engineering challenges were significant. A centerline elevator was supported on all four sides by the ship's structure. An edge-mounted elevator was supported primarily from one side, cantilevered out over the water. The structural loads were asymmetric, creating torsional stress on the support framework. The machinery had to be robust enough to handle these loads while remaining light enough not to compromise the ship's stability. The platform itself had to be large enough to accommodate contemporary aircraft, which meant roughly 60 feet by 34 feet, weighing several tons even before accounting for the weight of an aircraft sitting on it. The Bureau of Ships and the chief engineer of the Otis Elevator Company spent months designing the mechanism. They settled on a T-shaped platform, with the main section sized for an aircraft's main landing gear and an outrigger for the tailwheel. Two massive arms extending from the ship's side moved the platform in a curved arc, swinging it up from the hangar deck level to the flight deck level, or down for hangar access. The motion was different from centerline elevators, which moved straight up and down. The deck edge elevator traced a curved path, requiring different control systems and safety interlocks. When Wasp went to sea in June 1940 for her shakedown cruise, the deck edge elevator worked. Not perfectly at first. There were teething problems with the hydraulics and some concerns about platform stability in heavy seas, but it worked. More importantly, it demonstrated something that would prove revolutionary. When the elevator was in the down position, the flight deck remained intact. There was no hole. The deck edge elevator, by virtue of being mounted outside the normal flight deck contours, didn't interrupt the primary operating surface when it descended to hangar deck level. This might seem like a minor detail. It wasn't. It meant that flight operations could continue regardless of elevator position. Launch aircraft while the elevator was bringing up reinforcements from the hangar deck. Recover aircraft while the elevator was taking damaged planes below for repairs. The flight deck was no longer punctuated by movable holes that had to be worked around. It was a continuous surface, only getting larger when the elevator rose to deck level, providing additional parking space outside the normal ship's beam. The Navy watched Wasp's performance with intense interest. Battle damage wasn't the immediate concern in 1940. War in Europe was raging, but America remained officially neutral. The question was efficiency. Could a deck edge elevator handle the operational tempo of sustained flight operations? The answer became clear during Wasp's deployment to the Atlantic in 1941 and early 1942. The ship operated continuously, first on neutrality patrol, then supporting the British home fleet, eventually ferrying Spitfire fighters to Malta. During one remarkable mission in April 1942, Wasp loaded 47 Supermarine Spitfires in her hangar deck at Gibraltar. The aircraft were too large to fit on the centerline elevators of most American carriers. But Wasp's deck edge elevator, combined with her centerline elevators, allowed her deck crew to bring all 47 aircraft up and spot them on the flight deck for launch. The operation took just over 2 hours. Every Spitfire got airborne. The deck edge elevator had moved aircraft continuously throughout the evolution, never interrupting flight deck operations, never creating a gap in the deck that had to be worked around. It was a continuous surface, only getting larger when the elevator rose to deck level, providing additional parking space outside the normal ship's beam. The Navy watched WASP's performance with intense interest. Battle damage wasn't the immediate concern in 1940. War in Europe was raging, but America remained officially neutral. The question was efficiency. Could a deck-edge elevator handle the operational tempo of sustained flight operations? The answer became clear during WASP's deployment to the Atlantic in 1941 and early 1942. The ship operated continuously, first on neutrality patrol, then supporting the British home fleet, eventually ferrying Spitfire fighters to Malta. During one remarkable mission in April 1942, WASP loaded 47 Supermarine Spitfires in her hangar deck at Gibraltar. The aircraft were too large to fit on the centerline elevators of most American carriers, but WASP's deck-edge elevator, combined with her centerline elevators, allowed her deck crew to bring all 47 aircraft up and spot them on the flight deck for launch. The operation took just over 2 hours. Every Spitfire got airborne. The deck-edge elevator had moved aircraft continuously throughout the evolution, never interrupting flight deck operations, never creating a gap in the deck that had to be worked around. It was a continuous surface, only getting larger when the elevator rose to deck level, providing additional parking space outside the normal ship's beam. The Bureau of Ships started redesigning carriers. By December 1939, preliminary designs for the Essex class were already incorporating lessons from early war experience. The new carriers would be larger than the Yorktown class, displacing over 30,000 tons fully loaded. They would carry 90 to 100 aircraft, and they would have 3 elevators, 2 centerline and 1 deck edge, mounted on the port side. The decision wasn't unanimous. Conservative naval architects argued that deck-edge elevators were inherently weaker than centerline designs, more vulnerable to storm damage, more likely to fail in heavy seas. Some carrier captains, including veterans who had commanded Yorktown-class ships, worried that the asymmetric weight distribution of a deck-edge elevator would affect ship handling or stability. The Panama Canal issue was raised repeatedly. Would a deck-edge elevator extending beyond the ship's normal beam prevent transit through the canal? The Bureau of Ships addressed each concern methodically. Structural analysis showed that proper engineering could make deck-edge elevators as strong as centerline designs while actually reducing maintenance requirements by approximately 20%. The simpler machinery, with fewer moving parts and less complex hydraulic systems, meant less could go wrong and repairs were faster when problems did occur. The Panama Canal, the solution was elegant. Design the elevator to fold. The platform could swing down alongside the hull, bringing the ship's beam back within canal clearance limits. The stability concerns proved unfounded. Testing with scale models and eventually with USS Essex herself demonstrated that the weight of a deck-edge elevator, while positioned off-centerline, was relatively minor compared to the ship's total displacement. The added weight could be compensated by ballast adjustments or, more practically, by reducing ballast requirements elsewhere, since the deck-edge elevator was lighter than an equivalent centerline design with its associated support structure extending deep into the ship. USS Essex, the lead ship of her class, laid down in Newport News shipbuilding in April 1941, incorporated the deck-edge design from the beginning. Her keel was barely in place when Pearl Harbor happened. Construction accelerated.
By the time Essex commissioned in December 1942, the Navy needed carriers desperately. Yorktown and Lexington were gone. Hornet would be lost at Santa Cruz in October. Wasp had been torpedoed off Guadalcanal in September. The fleet was hemorrhaging carriers faster than they could be replaced. Essex joined the Pacific Fleet in May 1943 with an air group of 90 aircraft. Her deck-edge elevator, positioned on the port side forward of the island, measured 60 feet by 34 feet. The platform could handle any aircraft in the Navy inventory, from the massive TBF Avenger torpedo bomber to the F-6F Hellcat fighter. Cycle time from hangar deck to flight deck was 45 seconds in automatic mode. A well-trained deck crew could complete a full cycle, aircraft on, up, aircraft off, next aircraft on, down, aircraft off, in under a minute. The operational advantages became apparent immediately during Essex's first combat operations against Marcus Island in August 1943. Her deck crews demonstrated what continuous elevator operation meant in practice. While aircraft were launching from the bow catapults and forward flight deck, the deck edge elevator was simultaneously bringing up additional aircraft from the hangar. There was no pause in operations, no waiting for a centerline elevator to finish its cycle before launching could resume. The flight deck remained a continuous working surface throughout the entire evolution. More importantly, battle damage to the deck edge elevator wouldn't cripple the ship. If the elevator was knocked out, the flight deck lost some additional parking space but remained intact. Aircraft could still launch and recover using the full length of the deck. The two centerline elevators provided hangar access. Operations would be degraded but not stopped. This redundancy, having three independent elevator systems instead of three elevators all requiring the same flight deck integrity, meant that Essex-class carriers could absorb significantly more damage while remaining mission-capable. The Essex class incorporated one additional innovation that compounded the deck edge elevator's advantages. The hangar deck had no armor above it. Instead, the armor was positioned below on the fourth deck. This decision was controversial. British carriers used armored hangar decks, accepting smaller air groups in exchange for better protection. But the American approach, combined with deck edge elevators, created something the British couldn't match: massive hangar volume with efficient aircraft flow. The unarmored hangar meant the supporting structure between the hangar deck and flight deck could be lighter. Less structural steel meant more room for aircraft elevators to move, for deck crews to work, for aircraft to be spotted efficiently. The deck edge elevator, not penetrating through armored decking, could be positioned and sized more flexibly. It added capability without subtracting protection from critical spaces, because those critical spaces were lower in the ship, below the hangar, protected by the armor belt and armored deck. The Essex-class carriers started arriving in theater throughout 1943 and 1944. Yorktown in April 1943, Intrepid in February 1944, Hornet in March, Wasp, the second carrier to bear that name, in November. Each ship carried the same basic design: 872 feet long, 108 feet wide at the beam, with a flight deck extending slightly beyond the hull, 3 elevators, 2 centerline, and 1 deck edge, 90 to 100 aircraft. Operational speed, 33 knots. The Navy standardized deck crew procedures across the class. Every Essex-class carrier ran the same choreography: land aircraft on the stern, immediately taxi them forward past the island, use the forward centerline elevator or deck edge elevator to strike them below for rearming and refueling, bring up the next launch cycle from the hangar using all 3 elevators simultaneously, spot aircraft on deck for launch, recover, repeat. The tempo was relentless, and the deck edge elevator made it sustainable. Task Force 58, the fast carrier task force that would become the Navy's primary striking arm in the Pacific, typically operated with 4 to 6 Essex-class carriers as its core. During the Marshall Islands campaign in early 1944, these carriers demonstrated sortie rates that would have been impossible with centerline elevators alone. Essex herself flew over 400 sorties in a 72-hour period during strikes on Kwajalein in August. The deck edge elevator operated continuously, moving damaged aircraft below, bringing up fresh aircraft, never pausing, never creating a gap in flight deck operations. The Japanese noticed. Intelligence reports from prisoners and captured documents indicated that Japanese naval planners had identified American carriers' ability to maintain sustained flight operations as a critical advantage. Japanese carriers, still using exclusively centerline elevator designs, couldn't match the tempo. Their deck crews had to pause operations to work around elevator cycles. Aircraft accumulated on deck, creating vulnerability. The Akagi, Kaga, and Soryu at Midway had all been caught with their decks crowded, unable to launch aircraft quickly enough, in part because their elevator arrangements restricted aircraft flow. By late 1944, with 24 Essex-class carriers built or under construction, the deck edge elevator had become the standard American carrier design feature. The Midway-class carriers, designed as armored fleet carriers displacing 45,000 tons, incorporated not one but two deck edge elevators, positioned on the port side forward and on the starboard aft, in addition to one centerline elevator. The asymmetry wasn't a problem. It was an advantage. Aircraft could be moved from hangar to flight deck on either side of the ship, allowing deck crews to route traffic based on operational needs rather than being constrained by elevator position. The proof of concept came repeatedly in combat. When USS Franklin took 2 bomb hits on March 19, 1945, while launching strikes near Japan, the bombs detonated on the flight deck and hangar deck, starting massive fires and secondary explosions. The centerline elevators were damaged, but the starboard deck edge elevator, added during a refit, remained functional. Franklin's crew used that single elevator to move firefighting equipment up and aircraft wreckage down, maintaining some ability to manage the crisis despite catastrophic damage to the rest of the ship. The carrier survived, in large part, because the deck edge elevator provided a pathway through the ship that remained usable when the centerline systems failed. USS Bunker Hill suffered similar damage on May 11, 1945, when 2 kamikazes hit within minutes of each other. The ship lost 346 men killed and another 264 wounded. Fires raged across the forward flight deck and the hangar deck. The forward centerline elevator was damaged and jammed in the down position, creating a 60-foot hole in the flight deck that channeled flames and smoke. The starboard deck edge elevator, positioned aft of the impact points, continued functioning. Damage control parties used it to evacuate wounded from the hangar deck and bring up firefighting equipment. The elevator itself became a refuge, a platform where burned and injured sailors could wait for evacuation while flames swept across the rest of the ship. These weren't designed functions. The deck edge elevator was meant to move aircraft, but its position outside the main hull structure, its independence from the centerline systems, its relative protection from blast effects channeled through centerline elevator wells, all these characteristics meant that it remained functional in conditions that destroyed conventional elevators. The redundancy wasn't accidental. It was the result of accepting that carriers would be hit, would be damaged, would need to keep fighting with degraded systems.
The Essex class suffered heavily during 1945. Kamikazes struck Essex, Intrepid, Yorktown, Ticonderoga, Franklin, Bunker Hill, and others. Bombs, torpedoes, and suicide aircraft killed thousands of American sailors. But not a single Essex-class carrier was sunk by enemy action during the war. Not one. They absorbed damage that would have destroyed earlier carriers and remained afloat, in large part because their damage control systems worked and the redundant elevator arrangements meant battle damage to one system didn't cripple the entire ship. Post-war analysis by the Naval Technical Mission to Japan examined captured Japanese carrier designs and operational doctrine. The reports noted that Japanese carriers, even the late-war designs like Taiho and Shinano, relied exclusively on centerline elevators. When these ships were hit, as Taiho was by submarine torpedoes in June 1944, the damage cascaded through the centerline elevator wells, spreading fire and flooding across multiple decks. The ships lacked the redundancy that deck edge elevators provided. They were, in the brutal calculus of naval architecture, more vulnerable to catastrophic damage from relatively modest hits. American carrier design had stumbled onto something fundamental. The deck edge elevator wasn't just a space-saving measure or a weight reduction scheme. It was a survivability feature, one that worked precisely because it violated the conventional wisdom of symmetrical design and centerline placement. By moving critical systems to the edge of the ship, where they seemed more vulnerable to storm damage and enemy fire, American designers had actually created a more resilient overall system. The apparent weakness was a strength. This pattern would repeat in other carrier innovations. The angled flight deck, developed by the British and adopted by the Americans in the 1950s, worked on the same principle. Separate landing and launch areas. Reduce single points of failure. Accept asymmetry in exchange for operational flexibility. The deck edge elevator paved the way for this thinking. It demonstrated that carriers didn't have to be perfectly symmetrical to be effective. They had to be adaptable, resilient, capable of continuing operations despite damage. The Essex class served far beyond World War II. 15 of the carriers underwent SCB-27 and SCB-125 modernizations in the 1950s, receiving angled flight decks, steam catapults, strengthened elevators, and updated electronics. During these refits, many ships had their aft centerline elevators removed and replaced with starboard deck edge elevators. The modernization explicitly recognized what combat experience had proven. Deck edge elevators were superior for jet operations. They provided better deck flow, better damage control, better operational flexibility. Several Essex-class carriers served in Vietnam. USS Hancock, USS Ticonderoga, USS Bonhomme Richard, USS Oriskany, USS Intrepid all launched strikes into North Vietnam using aircraft that weighed twice as much as World War II planes. The elevators designed in 1939 still worked. Some needed strengthening to handle heavier jets, but the basic design remained sound. The deck edge elevator, position unchanged, moved F-4 Phantoms and A-4 Skyhawks with the same efficiency it had moved F-6F Hellcats and SB-2C Helldivers 2 decades earlier.
The last Essex-class carrier, USS Lexington, served as a training carrier until 1991, 49 years after the class entered service. Her deck edge elevator, essentially unchanged from the original 1940s design, continued operating until the ship's final decommissioning, a 1940 innovation that worked in 1991. That almost never happens in military technology. Modern supercarriers trace their lineage directly to those Essex-class innovations. When the Navy designed the Forrestal class in the early 1950s, the first true supercarriers, deck edge elevators weren't optional, they were foundational. USS Forrestal, commissioned in October 1955, displaced 60,000 tons, more than twice an Essex. Her flight deck measured 1,039 feet by 252 feet. She carried an air wing of 90 aircraft. And she had 4 elevators, 3 of them deck edge. The Forrestal design represented a complete rethinking of carrier aviation around jet aircraft. Jets were heavier, faster, and more complex than the propeller aircraft of World War II. They needed more fuel, more maintenance, more deck space for operations. But the fundamental problem remained the same. You needed to move aircraft efficiently between the hangar deck and flight deck while maintaining flight operations. Centerline elevators still created holes in the deck. Deck edge elevators didn't. Forrestal's elevator arrangement became the template for every American supercarrier built afterward. One centerline elevator forward, positioned between the catapults, where it served as a staging area for launch operations. 3 deck edge elevators, 2 on the starboard side and 1 on the port side, positioned to maximize aircraft flow without interrupting the angled landing area. Because by 1955, carriers had another innovation that worked in perfect synergy with deck edge elevators: the angled flight deck. The angled deck, developed by the British Royal Navy in the early 1950s, solved a different problem. On straight-deck carriers, aircraft landed along the centerline, directly toward the bow. If a pilot missed the arresting wires, his aircraft crashed into planes parked forward, often with catastrophic results. The angled deck rotated the landing area 8 to 10 degrees to port, allowing missed approaches to simply fly off the angled section and go around for another attempt. But the angled deck only worked if you could keep the landing area clear, which meant you needed elevators that didn't interrupt the landing path. Deck edge elevators, positioned outside the angled landing area, provided exactly that capability. The starboard deck edge elevators on Forrestal sat forward and aft of the landing path, not interrupting it. The port deck edge elevator was positioned well forward of the angled section. Aircraft could land continuously on the angled deck while all three deck edge elevators operated simultaneously, moving aircraft up from the hangar or down for service. The two innovations, developed independently, complemented each other perfectly. The operational tempo this enabled was revolutionary. During USS Forrestal shakedown operations in 1955, the ship demonstrated sustained sortie rates that no World War II carrier could match. In one evolution off the Virginia Capes, Forrestal launched a 40-aircraft strike, recovered 32 aircraft from a previous mission, and launched a 20-aircraft combat air patrol, all within 47 minutes. 3 separate operations running simultaneously, because the deck geometry kept everything separated and the elevators never interrupted the landing area. Soviet naval planners had assumed American carriers were vulnerable during flight operations. Catch them while launching or recovering, and you could overwhelm their defenses. The Forrestal class with its angled deck and deck edge elevators destroyed that assumption. These carriers were never truly vulnerable because they were never truly stopped. They could launch, recover, and rearm continuously, maintaining constant combat capability. Admiral Sergei Gorshkov, commander of the Soviet Navy, wrote in a 1956 assessment that NATO carrier groups built around Forrestal-class ships could maintain continuous strike capability that the Soviet surface fleet had no effective counter against. His analysis was accurate. By the time the Forrestal class was complete, 4 ships in the late 1950s, the United States possessed a carrier force capable of projecting more sustained air power than any nation in history. The Kitty Hawk class, commissioned starting in 1961, followed the same basic design. 4 ships, each with 3 deck edge elevators positioned identically to Forrestal. USS America, the last of the class, commissioned in 1965, would serve until 1996, her deck edge elevators operating for 31 years without major redesign. The machinery was updated, hydraulics were improved, control systems were modernized, but the basic concept remained unchanged. 60-foot by 52-foot platforms, edge-mounted, serving aircraft that evolved from A-4 Skyhawks to F-14 Tomcats without requiring fundamental modifications. The nuclear-powered carriers followed the same pattern. USS Enterprise, CVN-65, commissioned in 1961, displaced 93,000 tons and carried 8 nuclear reactors. Her deck edge elevators were positioned and sized almost identically to Forrestal's. The Nimitz class, 10 carriers commissioned between 1975 and 2009, standardized the 3 deck edge elevator arrangement. Every Nimitz, from USS Nimitz herself to USS George H.W. Bush, carried elevators capable of lifting 74,000 pounds, sized at 85 feet by 52 feet, positioned on the starboard side, forward and aft, and on the port side, forward. These weren't afterthoughts or compromises. The deck edge elevator positions were determined early in the design process. Then everything else, catapults, arresting gear, hangar layout, weapons magazines, crew spaces, was arranged around them. The elevators defined aircraft flow patterns. Aircraft flow patterns defined sortie rates. Sortie rates defined combat capability. The chain of causation ran directly from elevator position to strategic effectiveness. USS Gerald Ford, commissioned in July 2017 as the lead ship of the newest carrier class, cost $13 billion and represents the most advanced naval engineering in history. She carries electromagnetic aircraft launch systems instead of steam catapults, advanced arresting gear with digital control, a nuclear reactor that will run for 50 years without refueling, automation that reduces crew requirements by several hundred sailors, and 3 deck edge elevators positioned almost as Forrestal's were in 1955. The Ford-class elevators are larger, 85 feet by 52 feet, capable of lifting heavier aircraft.
The machinery is updated using electromagnetic motors and advanced materials. But the geometry hasn't changed. Starboard side forward and aft, port side forward, all positioned outside the angled landing area. 70 years of technological advancement, and nobody's found a better arrangement. Because the arrangement was right the first time. Other nations copied the design wholesale. When China built Liaoning and Shandong, their first modern carriers, both ships included deck-edge elevators. India's Vikramaditya, converted from a Soviet Kiev-class carrier, received deck-edge elevators during the conversion specifically to improve aircraft flow. Even France's Charles de Gaulle, the only nuclear-powered carrier outside the United States Navy, uses 2 deck-edge elevators positioned to maximize flight deck utility.
The British took a different path with their Queen Elizabeth-class carriers. These ships operate F-35B Lightning II aircraft, short takeoff and vertical landing jets that don't require catapults or arresting gear. Theoretically, they don't need the same elevator arrangements as conventional carriers. But both Queen Elizabeth and Prince of Wales include deck-edge elevators anyway, positioned on the starboard side. Because the fundamental principle still applies. Even with VTOL aircraft, you need to move planes between decks efficiently without interrupting flight operations. The deck-edge elevator provides that capability better than any alternative. The design has outlasted the technology it was created for. The F-6F Hellcats and TBF Avengers that first rode Essex-class deck-edge elevators are long gone. So are the F-4 Phantoms that flew from Vietnam-era carriers, the A-6 Intruders, the F-14 Tomcats, the A-7 Corsairs, all retired. Today's carrier air wings fly FA-18 Super Hornets and F-35C Lightning IIs, fifth-generation aircraft with capabilities that would have seemed like science fiction in 1940. But they still ride the same elevators, positioned in the same locations, serving the same function. The maintenance burden proved remarkably manageable. Modern deck-edge elevators require approximately 80 man-hours per month in preventative maintenance, significantly less than the 500 hours World War II centerline elevators demanded. The machinery is simpler, more reliable, easier to access. Hydraulic systems have been replaced by electromagnetic drives on the Ford class, further reducing maintenance requirements. The Navy estimates that Ford-class elevators will require 40% fewer man-hours than Nimitz-class elevators while handling heavier aircraft loads. Combat experience validated the survivability advantages repeatedly. During the Vietnam War, USS Forrestal suffered a catastrophic fire on July 29, 1967, when a Zuni rocket accidentally fired on the flight deck, triggering explosions and fires that killed 134 sailors. The starboard deck edge elevators were damaged by blast effects, but the port deck edge elevator remained functional, providing a route to move firefighting equipment and evacuate wounded. The elevator's position, separated from the main fire zone, meant it survived conditions that destroyed equipment positioned closer to centerline. USS Enterprise, CVN-65, experienced a similar fire in January 1969 when a Zuni rocket exploded during ordnance loading operations. The fire killed 27 sailors and destroyed 15 aircraft. The starboard forward deck edge elevator was damaged, but the other 2 elevators continued operating, allowing damage control parties to fight the fire from multiple access points. The redundancy that deck edge elevators provided meant battle damage or accident damage to one system didn't paralyze the ship. Modern carriers operate with a tempo that would have been impossible with centerline elevators alone. During Operation Inherent Resolve against ISIS, USS Dwight D. Eisenhower maintained sortie rates of 75 missions per day for 7 consecutive months. That's over 16,000 sorties total. The deck-edge elevators cycled continuously, moving aircraft between missions, bringing up armed aircraft for launch, taking down aircraft needing maintenance, never stopping, never creating a gap in operations. The Navy doesn't track elevator cycle statistics separately, but carrier air wing commanders estimate that during sustained operations, each deck-edge elevator completes 60 to 80 cycles per day. That's one complete cycle,
aircraft up or down, every 15 to 20 minutes for 24 hours straight. The machinery runs continuously for months during deployments, subjected to salt water, temperature extremes, ship motion in heavy seas, and the constant stress of moving 70,000-pound aircraft. And it works. There's something remarkable about how an innovation born from desperation and treaty limitations became the standard design for the world's most powerful warships. USS Wasp's deck-edge elevator, installed in 1940 as an experiment to save weight and space, established the template that every supercarrier would follow. The engineers who designed it probably didn't envision F-35 Lightning IIs, or electromagnetic catapults, or carriers displacing 100,000 tons. They were solving the immediate problem of how to operate aircraft efficiently from a 14,000-ton hull constrained by treaty limitations. But they stumbled onto something fundamental about carrier design. Position critical systems where they enhance rather than interrupt operations. Accept asymmetry if it provides redundancy. Design for damage, not just for ideal conditions. These principles, validated in combat from Guadalcanal to Okinawa, from Korea to Vietnam to the Persian Gulf, remain relevant precisely because they address physics and geometry, not specific technologies. Aircraft will always need to move between decks. Flight decks will always need to remain clear for operations. These facts don't change regardless of whether aircraft are propeller-driven or jet-powered or whatever comes next. The deck-edge elevator doubled carrier sortie rates, not through any single dramatic improvement, but through the accumulation of small advantages. No hole in the flight deck went down. Additional parking space went up. Simpler maintenance. Better damage control, independent operation from centerline systems. Each advantage seemed modest. Together, they transformed carrier aviation from a platform that could launch one major strike per day into a weapon system capable of continuous, sustained operations, limited only by aircrew endurance and aircraft availability. Stand on the flight deck of USS Gerald R. Ford today, and you're looking at geometry that USS Wasp pioneered 85 years ago. The elevators are larger, the machinery is more sophisticated, the aircraft are incomparably more capable. But the basic principle remains identical. Move aircraft efficiently between decks without interrupting the primary operating surface. It's a solution so simple and so effective that nobody's improved on it in nearly a century of trying. Lieutenant Junior Grade Shunsuke Tomiyasu couldn't have known in the final seconds of his life that the elevator he destroyed would help prove the necessity of the innovation that would replace it. Enterprise's forward centerline elevator, blown 400 feet into the air, demonstrated exactly why centerline elevators were vulnerabilities. They created structural discontinuities that catastrophic damage could exploit. They concentrated critical functions in single locations that enemy action could neutralize. They were, in the brutal calculus of naval architecture, single points of failure. The Essex-class carriers that avenged Enterprise, that fought through the last months of the war and served for decades afterward, succeeded in part because they didn't have that vulnerability. The innovation saved lives, enabled operations, and established a design principle that would govern carrier construction for the next 8 decades. There's a certain irony in how the solution to Enterprise's vulnerability was already serving in the fleet when she was hit. Essex-class carriers with their deck-edge elevators were operating in the same task force, launching strikes from the same ocean, proving every day that the better design existed. Enterprise represented the old way of building carriers, magnificent and powerful, but fundamentally constrained by design decisions made in the 1920s. Essex represented the future, a future where carriers could absorb damage, continue fighting, and adapt to technologies that didn't exist when their keels were laid. The deck-edge elevator wasn't the only innovation that made modern carriers possible. Steam catapults, angled decks, optical landing systems, nuclear propulsion all contributed, but the deck-edge elevator enabled those other innovations to work. You can't operate an angled deck effectively if your elevators interrupt the landing area. You can't maintain sustained sortie rates if your elevators create holes in the flight deck.
You can't build carriers for survivability if critical systems create single points of catastrophic failure. The morning of May 14, 1945, Enterprise steamed into history as the most decorated warship of World War II. Her forward elevator rocketing into the sky marked the end of her combat career. But it also marked a transition point in carrier design, the moment when the vulnerabilities of centerline elevators became undeniable, and the advantages of deck-edge designs became doctrine. Today, every operational aircraft carrier in the United States Navy carries deck-edge elevators positioned where USS Wasp's single experimental elevator proved the concept 85 years ago. That continuity, from a treaty-constrained experiment to the most powerful warships ever built, represents something rare in military technology. A solution so correct, so fundamental, so aligned with the underlying requirements of the mission that it never needed replacing, just refinement, just improvement, never reinvention.
The 15-ton elevator platform that Lieutenant Tomiyasu's kamikaze blasted 400 feet into the air proved why centerline elevators had to go. The deck-edge elevators that replaced them proved why sometimes the answer to complex problems isn't more complexity. It's better geometry, smarter positioning, and accepting that perfection often looks asymmetrical. In the decades since Enterprise withdrew from combat, carrier aviation has evolved beyond anything her designers could have imagined. Jet aircraft traveling at supersonic speeds, precision-guided munitions with laser and GPS guidance, radar systems that can track hundreds of targets simultaneously, satellite communications that allow coordination across thousands of miles. But through all that change, through all that advancement, the fundamental method of moving aircraft between the hangar deck and flight deck remains essentially unchanged. Deck-edge elevators positioned outside the primary operating surface, providing redundancy and resilience, enabling continuous operations. It's a testament to the brilliance of the original design that it has adapted to 7 decades of technological change without requiring fundamental modification. The elevators are larger now, stronger, more automated, but they're in the same place, doing the same job, solving the same problem. When the Navy designs its next generation of carriers, whatever form they take, whatever technologies they incorporate, they will almost certainly include deck-edge elevators, because some solutions are so good, so fundamentally correct, that they transcend the era that created them. The men who died on Enterprise on May 14, 1945, the 14 killed instantly in the explosion, and the others who died later from their wounds, gave their lives proving a point that naval architects had been arguing for years. Centerline elevators were a vulnerability that no amount of armor or damage control could fully mitigate. Their sacrifice, and the sacrifice of thousands of other carrier sailors who died in similar attacks throughout the war, drove the innovation that would make future carriers safer, more capable, more resilient. The deck-edge elevator didn't just improve carrier operations, it saved lives by creating redundancy and eliminating single points of catastrophic failure. Every carrier sailor who has served since 1945 owes a debt to those early designers who looked at conventional wisdom and decided there had to be a better way. To the engineers who took a risk on asymmetric design when symmetry was the accepted standard. To the shipyard workers who built elevators that extended beyond the hull when everyone said it couldn't be done safely. To the deck crews who learned to operate the new systems and proved they worked better than the old ones. And to the men like Lieutenant Tomiyasu, whose final act of war inadvertently demonstrated the vulnerability that the new design would eliminate. War drives innovation in brutal ways, teaching lessons written in blood and steel, proving concepts through destruction rather than theory. The deck-edge elevator stands as one of those innovations that emerged from the crucible of combat and proved so effective that it became permanent. A solution born from treaty restrictions and weight limitations that turned out to be superior to conventional designs in every meaningful way. USS Enterprise, the Big E,
The most decorated ship in American naval history earned 20 battle stars and a Presidential Unit Citation. It fought at Midway, at Guadalcanal, at the Philippine Sea, at Leyte Gulf. It was hit repeatedly, damaged severely, but always returned to fight again. Until that morning in May 1945, when a single, well-placed kamikaze finally succeeded in doing what the entire Japanese Navy had tried and failed to do for 4 years. Not sinking her, but putting her out of action permanently. The hole in her flight deck was just too large, the damage too extensive, the war too close to its end to justify the months of repair work she would need. She steamed to Puget Sound Naval Shipyard, underwent temporary repairs, and then served briefly in Operation Magic Carpet, bringing American servicemen home from the Pacific. She was decommissioned in February 1947, less than 2 years after that final kamikaze strike. The Navy wanted to preserve her as a museum, a permanent memorial to her achievements, but the cost was prohibitive in the post-war budget cuts. Despite passionate advocacy from veterans groups and members of Congress, Enterprise was sold for scrap in 1958. She was broken up in New Jersey, reduced to steel that would be recycled into new ships, new buildings, new infrastructure. Her legacy lived on in different form. The 9th ship to bear the name Enterprise, CVN-65, the world's first nuclear-powered aircraft carrier, commissioned in 1961. She served for 51 years, longer than any carrier in history, and she carried deck-edge elevators, positioned where USS Wasp had proven they belonged 2 decades earlier. The 10th Enterprise, CVN-80, is under construction now. She's a Ford-class carrier that will incorporate every lesson learned from 8 decades of carrier aviation. And she will have 3 deck-edge elevators in the same positions, serving the same function, continuing an innovation that began with a desperate attempt to save weight on a treaty-limited carrier in 1940. From Wasp to Enterprise to Ford, the lineage is direct and unbroken. A design that worked in 1940 still works in 2024, that will still work in 2050 when CVN-80 reaches the fleet, that will likely still work in 2100 when carriers we haven't imagined yet sail oceans defending interests we can't predict. Because some innovations transcend their origins, some solutions are so fundamentally correct that they become eternal. The deck-edge elevator is one of those solutions, born from limitation, proven in combat, refined through experience, but never replaced because replacement would mean accepting something inferior to what already exists. Lieutenant Junior Grade Shunsuke Tomiyasu died in the explosion when his Zero hit Enterprise. He was 23 years old. In that final moment, diving inverted toward the American carrier, he succeeded in his mission. He struck the ship, detonated his bomb, killed American sailors, and forced the most famous carrier in the Pacific to withdraw from combat. But in a larger sense, he failed. Because Enterprise withdrawing didn't change the outcome of the war. The Essex-class carriers with their deck-edge elevators were already in theater, already launching strikes, already demonstrating that the future of carrier aviation had evolved beyond what Enterprise represented. The innovation that would define carrier design for the next century was already proven, already deployed, already winning the war. One more carrier knocked out of action didn't matter, because the industrial might of the United States had produced 20 dozen improved carriers that had learned from Enterprise's vulnerabilities and eliminated them through better design. That's the story of the deck-edge elevator. Not a dramatic innovation that changed warfare overnight, but a quiet improvement that accumulated advantages until those advantages became overwhelming. A solution that worked so well it never needed replacement. A design that proved its worth in combat and then continued proving it for 85 years and counting. Stand on the flight deck of any American carrier today and look at those elevators positioned on the sides of the ship, rising from the hangar deck to the flight deck, never interrupting operations, always providing redundancy, enabling continuous sustained air operations that no adversary can match. That's the legacy of USS Wasp's experimental elevator. That's the lesson Enterprise's destroyed elevator taught. That's the future that deck-edge elevators enabled. Simple, effective, eternal.
Some solutions are just right.